My dear students, welcome back to our channel. In this video, I will be explaining the BSc 5th semester subject Chemistry, Spectroscopy and Chromatography as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 1 first important short question is: write about types of molecular spectra briefly. Answer: types of molecular spectra, simple explanation. When molecules absorb or emit energy, they produce different molecular spectra. These spectra help us understand the structure and energy of molecules. The three main types are: 1. Rotational spectra, microwave region. Molecules rotate around their axis. When they absorb microwave radiation, the rotational energy changes. Example: hydrogen chloride, HCl, shows a rotational spectrum used to find its bond length. 2. Vibrational spectra, infrared region. Atoms in a molecule vibrate like springs. Absorbing infrared, IR, light causes these vibrations to change. Example: water, HO, and CO show IR spectra used to identify functional groups. 3. Electronic spectra, UV visible region. Here, electrons jump between energy levels when UV or visible light is absorbed. Example: colored compounds like potassium permanganate show electronic transitions, giving them their color. Easy tip to remember. RV: rotational, microwave, vibrational, IR, electronic, UVvis, each shows motion of rotation, vibration and electron respectively. Next important short question is: 2. Discuss the principle and selection rules of IR spectroscopy. Answer: principle and selection rules of IR spectroscopy. Principle: infrared, IR, spectroscopy is based on the fact that molecules absorb IR radiation and convert it into vibrational energy. Every bond in a molecule acts like a tiny spring. When IR light of the right frequency hits, the bond starts stretching or bending. The amount of energy absorbed gives information about the type of bond and functional group present. Selection rule: for a molecule to show an IR spectrum, there must be a change in dipole moment during vibration. Allowed transition, delta V is equal to plus or minus 1, means vibration changes by one level. If no dipole change occurs, like in O or N, the molecule is IR inactive. Example: carbon dioxide, CO, absorbs IR because its bending vibrations change the dipole moment, while nitrogen, N, does not. Easy tip to remember. IR active dipole must move. Only vibrating bonds with changing dipoles absorb IR radiation. Next important short question is: 3. Write about fingerprint region of infrared spectrum. Explain its significance. Answer: fingerprint region of infrared spectrum and its significance. In an infrared, IR, spectrum, the region between 1500 cm superscript 1 and 400 cm superscript 1 is called the fingerprint region. It is named so because, just like human fingerprints, each molecule has a unique pattern of absorption lines in this region. This area arises due to complex bending and stretching vibrations of bonds within the molecule. Even if two compounds have the same functional group, their fingerprint regions will look different, helping scientists identify them easily. Significance: used to confirm the identity of a compound by matching its IR spectrum with a reference. Helps distinguish isomers or compounds with the same groups but different arrangements. Example: ethanol and dimethyl ether both have CO bonds, but their fingerprint regions are completely different. Easy tip to remember. 1500 to 400, your molecule's fingerprint door. Each compound's unique IR pattern helps identify it just like a fingerprint. Next important short question is 4. Define and explain chromophore and oxochrome. Give example, V.IMP. Answer, chromophore and oxochrome. A chromophore is the part of a molecule that is responsible for its color. It absorbs light in the visible or UV region, causing electronic transitions. When light falls on the molecule, the chromophore absorbs certain wavelengths and reflects others, giving the compound its color. Common chromophores include groups like C is equal to C, C is equal to O, N is equal to N, and NO. Example, the N is equal to N azo group in methyl orange gives it an orange color. An oxochrome is a group that itself doesn't cause color, but when attached to a chromophore, it intensifies the color or shifts the absorption wavelength. Oxochromes donate or withdraw electrons, affecting how the chromophore absorbs light. Examples of oxochromes: OH, NH, OCH. Example, when OH is attached to a benzene ring, chromophore, it forms phenol, which is slightly colored. Easy tip. Chromophore gives the color, oxochrome makes it stronger. Next important short question is 5. Define the terms absorbance, transmittance, molar absorptivity in absorption spectroscopy. Answer, absorbance, transmittance, and molar absorptivity. In absorption spectroscopy, light passes through a sample and part of it is absorbed. 3 important terms describe this process. 1. Transmittance, T. It is the fraction of light that passes through the sample. T is equal to I0, where I0 is equal to intensity of light entering and I is equal to intensity leaving. If 70% of light passes, transmittance is equal to 0.7. 2. Absorbance, A. It measures how much light is absorbed by the sample. A is equal to log T. Higher absorbance means more molecules are absorbing light. 3. Molar absorptivity, epsilon. 3. Molar absorptivity, epsilon. It shows how strongly a substance absorbs light at a given wavelength per concentration and path length. It is given by Beer-Lambert law. A is equal to epsilon Cl, where C is equal to concentration, L is equal to path length. Easy tip. Transmittance tells what passes, absorbance tells what's lost, and molar absorptivity tells how strong the boss. Next unit 1. Long questions. First important long question is: explain various types of molecular spectra in detail. Answer, types of molecular spectra, detailed explanation. Molecular spectra are produced when molecules absorb or emit energy in the form of electromagnetic radiation. These spectra help scientists understand the structure, bonding, and energy levels of molecules. Depending on how molecules absorb energy, there are mainly 3 types of molecular spectra: rotational, vibrational, and electronic. 1. Rotational spectra. Found in the microwave region, 1010 superscript 1 superscript 1 Hz. Produced when molecules rotate and change their rotational energy levels. Only polar molecules, like HCl, CoHO, show rotational spectra. These spectra are a series of closely spaced lines. Use helps determine bond lengths and molecular shapes. Example, HCl shows a rotational spectrum that tells us about the distance between H and Cl atoms. 2. Vibrational spectra. Found in the infrared, IR, region, 4000 to 400 cm superscript 1. Produced when molecules vibrate, stretch or bend bonds. Each molecule has characteristic vibration frequencies like a fingerprint. Use helps identify functional groups in organic compounds. Example, the O group shows a broad absorption near 3400 cm superscript 1 in ethanol. 3. Electronic spectra. Found in the visible and ultraviolet UV region. Produced when electrons in molecules jump between electronic energy levels. These spectra often appear as bands due to combined electronic, vibrational, and rotational transitions. Use determines molecular structure, color, and purity. Example, the orange color of beta-carotene comes from its electronic transitions. Summary table. Type of spectrum region cause example application. Rotational microwave rotation HCl bond length. Vibrational infrared vibration ethanol functional groups. Electronic UV visible electron transition beta-carotene color and structure. Easy tip to remember. Rotivibe rotation, vibration, electron transition. These three types make up the colorful and informative world of molecular spectra. Next important long question is: 2. What is moment of inertia? Give the classification of molecules based on it. Answer: moment of inertia and classification of molecules. Moment of inertia, I, is a measure of a molecule's resistance to rotation about an axis. It depends on the mass of the atoms and their distance from the axis of rotation. Think of it like a spinning wheel. The further the mass is from the center, the harder it is to rotate. Mathematically, I is equal to MI/2, where Mi is equal to mass of the ith atom, Re is equal to distance of that atom from the rotation axis. Importance in rotational spectroscopy. The rotational energy levels of molecules depend on their moment of inertia. Measuring the rotational spectrum allows us to calculate bond lengths in diatomic molecules like HCl or Co. Classification of molecules based on moment of inertia. Molecules can be classified according to the number of rotational axes and the values of moments of inertia I_B, I_C along these axes. 1. Linear molecules. Molecules where all atoms lie in a straight line. Rotation occurs about axis perpendicular to the bond axis. Example, HCl, Co. Moments of inertia, I is equal to 0, I_B is equal to I_C is not equal to 0. 2. Spherical top molecules. Symmetrical in all directions, all three moments equal. Example, CH, methane, SF. I is equal to I_B is equal to I_C. 3. Symmetric top molecules. Two moments of inertia are equal, the third is different. Example, NH, ammonia, CHCl. I is equal to I_B is not equal to I_C. 4. Asymmetric top molecules. All three moments of inertia are different. Example, HO, water, HCO, formaldehyde. I is not equal to I_B is not equal to I_C. Easy tip to remember. Linear straight, spherical equal, symmetric to equal, asymmetric all different. Knowing the moment of inertia and molecular type helps in understanding rotational spectra and calculating bond lengths, making it a key concept in microwave spectroscopy. This way, with just I values and geometry, you can predict and explain the rotational behavior of molecules. Next important long question is: 3. Discuss different types of vibrations in polyatomic molecules. Answer: types of vibrations in polyatomic molecules. Molecules are not rigid, they vibrate continuously. In polyatomic molecules, molecules with more than 2 atoms, these vibrations are more complex than in diatomic molecules. Each vibration corresponds to a normal mode, which is a pattern of atomic motion where all atoms move periodically. Number of vibrational modes. For a molecule with n atoms, linear molecules, number of vibrational modes is equal to 3 and 5. Non-linear molecules, number of vibrational modes is equal to 3 and 6. Example. Co-linear, 3 atoms, 3 times 3 5 is equal to 4 vibrational modes. HO, non-linear, 3 atoms, 3 times 3 6 is equal to 3 vibrational modes. Types of vibrations. 1. Stretching vibrations. Change in bond length along the bond axis. 2 types. A. Symmetric stretching, all bonds stretch contract together. B. Asymmetric stretching, bonds stretch and contract alternately. O. Example, in HO, OH bonds stretch symmetrically or asymmetrically. 2. Bending vibrations. Change in bond angle between atoms. Types. A. Scissoring, 2 atoms move toward and away from each other like scissors. B. Rocking, atoms move in the same direction in the plane. C. Wagging, atoms move up and down out of plane. D. Twisting, atoms rotate in opposite directions out of plane. Example, in HO, bending vibrations cause the H-OH angle to change. Significance. Each vibrational mode absorbs IR radiation at a characteristic frequency, giving a unique fingerprint for molecules. Helps identify functional groups and study molecular geometry and bonding. Easy tip to remember. Stretch bonds, bend angles, symmetric asymmetric, scissor rock wag twist. By counting 3 and 5 or 3 and 6 modes and understanding the type of vibration, you can predict IR absorption bands and interpret the spectra of polyatomic molecules effectively. Next important long question is: 4. Describe the energy levels of a harmonic oscillator and discuss the selection rules and force constant, K, calculations in infrared spectroscopy. Answer: energy levels of a harmonic oscillator, selection rules, and force constant in IR spectroscopy. In infrared, IR, spectroscopy, molecular vibrations are often modeled as a harmonic oscillator, like a spring connecting two atoms. The atoms vibrate around an equilibrium bond length, storing energy in discrete quantized levels. Energy levels of a harmonic oscillator. The energy of a vibrating bond is given by EV is equal to V plus a half HV. V is equal to 0, 1, 2 vibrational quantum number. H is equal to Planck's constant. V is equal to vibrational frequency. The lowest energy, V is equal to 0, is 0 point energy. The molecule still vibrates even at absolute zero. Example, for HCl, the bond vibrates with a certain frequency and energy levels are spaced equally in the harmonic approximation. Selection rules. IR active vibration, the bond must have a changing dipole moment. Allowed transition, delta V is equal to plus or minus 1, the molecule can move only one level up or down. This is why some vibrations in molecules like N or O, nonpolar, do not appear in the IR spectrum. Force constant, K, calculations. The force constant, K, measures bond strength. Stronger bonds vibrate at higher frequencies. It is calculated using the vibrational frequency. V is equal to 1 to pi, K mu. V is equal to vibrational frequency. Mu is equal to reduced mass of atoms. Mu is equal to m_1 m_2 m_1 plus m_2. K is equal to force constant. Example, C is equal to O bond has a higher K, tilde 1600 nm than C tilde 500 nm, so its IR absorption occurs at a higher wave number, tilde 1700 cm superscript 1. Easy tip to remember. Energy levels, 0 point always present, selection delta V is equal to plus or minus 1, stronger bonds vibrate faster, higher frequency, higher force constant. By understanding energy quantization, selection rules, and force constant, IR spectroscopy allows us to identify bonds, measure bond strength, and interpret molecular vibrations effectively. Next important long question is: 5. Illustrate different types of electronic transitions, sigma sigma asterisk, n sigma asterisk, n pi asterisk, pi pi asterisk, with examples, and explain the terms chromophore and oxochrome. Answer: types of electronic transitions and chromophore and oxochrome. In electronic, UV spectroscopy, molecules absorb light, causing electrons to jump from a lower energy orbital to a higher energy orbital. These jumps are called electronic transitions. The main types are: 1. Sigma sigma asterisk. Electron moves from a bonding sigma orbital to an antibonding sigma asterisk orbital. Requires high energy, usually in the far UV region. Example: ethane, CH bonds. 2. N sigma asterisk. Electron from a non-bonding, lone pair, orbital jumps to an antibonding sigma orbital. Energy is lower than sigma sigma asterisk, occurs in near UV. Example: alcohols, O, and amines, NH. 3. N pi asterisk. Electron from a non-bonding, lone pair moves to an antibonding pi orbital. Common in compounds with C is equal to O or C is equal to N groups. Example: carbonyl compounds like formaldehyde, HC is equal to O. 4. Pi pi asterisk. Electron from a bonding pi orbital jumps to an antibonding pi asterisk orbital. Occurs in conjugated double bonds and aromatic compounds. Example: ethene, C is equal to C, benzene, beta-carotene. Chromophore and oxochrome. Chromophore, the part of the molecule responsible for color or light absorption. It contains double bonds or conjugated systems. Example: C is equal to C, C is equal to O, N is equal to N. Oxochrome, a group that doesn't absorb light alone but enhances or shifts the absorption of a chromophore. Usually electron donating or withdrawing groups. Example: O, NH, OCH. Example combined. In p-nitrophenol, the NO is a chromophore and O is an oxochrome. Together, they give a strong yellow color. Easy tip to remember. Sigma needs more energy, lone pairs less, pi bonds absorb visible chromophore colors, oxochrome boosts it. This knowledge helps predict UV spectra, colors of compounds, and the effect of substituents on absorption.